Voltage drop calculations are crucial in electrical system design. In the scenario presented, there are three transformers: a utility transformer, a step-up transformer, and a step-down transformer. The initial voltage drop calculations are stated as follows. The utility transformer has a 0.58% voltage drop, the step-up transformer has a 1.97% voltage drop, and the step-down transformer has a 0.58% voltage drop. This totals to a 3.13% voltage drop before even considering the main feeders and branch circuits within the building. The NEC, or National Electrical Code, sets guidelines for acceptable voltage drop. The code stipulates that the total voltage drop from the source, which is the transformer in this case, to the farthest point of utilization, should not exceed 5%. This 5% limit encompasses the voltage drop in both the feeders and the branch circuits. Given the existing 3.13% voltage drop due to the transformers, this leaves only 1.87% allowable voltage drop for the main feeders and branch circuits to comply with the NEC. There are several alternatives and suggestions to address this issue and potentially reduce voltage drop. Firstly, increasing the transformer size might help. A larger transformer generally has a lower impedance, which results in a lower voltage drop for the same load. However, it's important to consider the cost implications, as larger transformers are more expensive. Secondly, reducing the distance between transformers can significantly decrease voltage drop. Voltage drop is directly proportional to the length of the conductor. By placing the step-up transformer closer to the utility transformer and the step-down transformer closer to the building, the conductor lengths are reduced, thereby reducing the overall voltage drop. Thirdly, using aluminum conductors can be an option. Aluminum conductors have a higher resistance per unit length compared to copper, but they are also lighter and less expensive. In some cases, using larger aluminum conductors can be a cost-effective way to reduce voltage drop, but careful calculations must be performed to ensure that the ampacity and voltage drop are within acceptable limits. Fourthly, paralleling conductors is a technique to reduce the effective resistance of the circuit. By using multiple conductors in parallel for the same circuit, the current is divided among the conductors, reducing the current in each conductor and consequently reducing the voltage drop. Fifthly, installing voltage regulators can automatically compensate for voltage dropped. Voltage regulators maintain a constant output voltage despite variations in the input voltage or load current. They can be placed at strategic locations in a distribution system to boost the voltage and ensure that the voltage at the point of utilization is within the acceptable range. To ensure compliance with the NEC code, it is essential to verify that the combined voltage drop from the main feeders and branch circuits does not exceed the remaining 1.87%. This can be achieved by implementing one or more of the previously mentioned alternatives. It's also crucial to consider that the voltage drop calculations provided are based on nominal voltages. Actual voltage drops may vary depending on the load conditions. Higher loads will result in higher voltage drops. Therefore, it's recommended to perform voltage drop calculations under various load scenarios to ensure that the voltage drop remains within acceptable limits under all operating conditions. To accurately calculate voltage drop, several factors must be considered. These include the conductor material, length, cross-sectional area, current, and power factor. The voltage drop can be calculated using the following formula: voltage drop equals current times resistance times length, where the resistance is dependent on the conductor material and cross-sectional area. For alternating current circuits, the power factor also plays a role in voltage drop calculations. A lower power factor results in a higher current for the same amount of power, which in turn increases the voltage drop. Therefore, it's important to consider the power factor of the load when calculating voltage drop in alternating current circuits. Here are some additional considerations for reducing voltage drop in electrical systems. 1. Use appropriately sized conductors. Refer to NEC Table 310.16 to determine the appropriate conductor size for the anticipated load current. Increasing the conductor size reduces its resistance, thereby reducing voltage drop. 2. Minimize conductor length. Shorter conductors have lower resistance and therefore lower voltage drop. Plan the layout of the electrical system to minimize the distance between the source and the load. 3. Improve the power factor. A low power factor increases the current drawn by the load, which increases voltage drop. Correct the power factor by using power factor correction capacitors. 4. Use separate circuits for different loads. Avoid overloading circuits by distributing the load among multiple circuits. This reduces the current in each circuit, thereby reducing voltage drop. 5. Consider using a 240-volt system instead of a 120-volt system. For the same amount of power, a 240-volt system draws half the current of a 120-volt system, which significantly reduces voltage drop. 6. Ensure proper connections. Loose or corroded connections increase resistance, which increases voltage drop. Use proper connectors and ensure that all connections are tight and clean. 7. Perform regular maintenance. Inspect the electrical system regularly to identify and correct any potential problems such as loose connections or corroded conductors. 8. Consider using voltage-regulated power supplies. Voltage-regulated power supplies maintain a constant output voltage despite variations in the input voltage or load current. This can help to mitigate the effects of voltage drop on sensitive electronic equipment. 9. Use step-down transformers close to the load. If the voltage needs to be stepped down, place the step-down transformer as close to the load as possible to minimize the voltage drop in the low-voltage conductors. 10. Consider using a three-phase system instead of a single-phase system. Three-phase systems are more efficient and can deliver more power with lower voltage drop compared to single-phase systems. It is always advisable to consult with a licensed electrician for specific recommendations and to ensure compliance with all applicable codes and standards. A qualified electrician can perform a thorough assessment of the electrical system and provide tailored solutions to minimize voltage drop and ensure safe and reliable operation. Remember to always prioritize safety when working with electrical systems. De-energize circuits before working on them and follow all applicable safety precautions. Electrical work should only be performed by qualified individuals. In addition to the above suggestions, consider the following points for the specific airport project. 1. Analyze the load requirements carefully. Determine the actual power consumption of the remote building and ensure that the transformer is adequately sized to handle the load. Overestimating the load can lead to unnecessary expenses, while underestimating the load can result in voltage drop and other problems. 2. Evaluate the cost-effectiveness of different solutions. Consider the cost of each alternative, including the cost of materials, labor, and installation. Choose the solution that provides the best balance of performance and cost. 3. Consider the long-term implications of each solution. Some solutions, such as using aluminum conductors, may have lower upfront costs but may require more maintenance in the long run. Choose a solution that is sustainable and cost-effective over the long term. 4. Consult with the local utility company. The utility company may have specific requirements or recommendations for the electrical system. Consult with them to ensure that the design meets their requirements and is compatible with their grid. 5. Obtain all necessary permits and approvals. Ensure that the electrical system complies with all applicable codes and standards and obtain all necessary permits and approvals before starting construction. 6. Document the electrical system thoroughly. Keep accurate records of the electrical system, including drawings, specifications, and calculations. This documentation will be helpful for future maintenance and troubleshooting. 7. Train personnel on the operation and maintenance of the electrical system. Ensure that personnel who will be operating and maintaining the electrical system are properly trained on its operation and maintenance. This will help to prevent problems and ensure safe and reliable operation. 8. Conduct regular inspections and testing. Inspect and test the electrical system regularly to identify and correct any potential problems. This will help to prevent failures and ensure safe and reliable operation. 9. Have a contingency plan in place. Develop a contingency plan in case of a power outage or other electrical emergency. This plan should include procedures for restoring power and ensuring the safety of personnel. 10. Stay up to date on the latest electrical codes and standards. Electrical codes and standards are constantly evolving. Stay up to date on the latest codes and standards to ensure that the electrical system complies with the latest requirements. When selecting conductors, consider the following factors. 1. Ampacity. The conductor must be able to carry the anticipated load current without overheating. Refer to NEC Table 310.16 for conductor ampacity ratings. 2. Voltage drop. The conductor must have a low enough resistance to limit voltage drop to acceptable levels. Use voltage drop calculators to determine the appropriate conductor size. 3. Insulation. The conductor insulation must be suitable for the environment in which it will be installed. Consider factors such as temperature, moisture, and exposure to chemicals. 4. Flexibility. The conductor must be flexible enough to be easily installed and routed. 5. Cost. The conductor must be cost-effective for the application. Consider the cost of materials, labor, and installation. 6. Availability. The conductor must be readily available from suppliers. 7. Approvals. The conductor must be approved by a recognized testing laboratory such as Underwriters Laboratories or Canadian Standards Association. 8. Size. The conductor must be sized correctly for the application. Undersized conductors can overheat and cause fires, while oversized conductors can be more expensive and difficult to install. 9. Material. Conductors are typically made of copper or aluminum. Copper has a lower resistance than aluminum, but aluminum is lighter and less expensive. 10. Stranding. Conductors can be solid or stranded. Stranded conductors are more flexible than solid conductors and are easier to install.